Hello, once more, welcome back to the desk. This is the third part of the custom DCC function decoder series. In this episode we're going to take our project from this, which flashes the light when it's powered by track power, to this, being able to respond to DCC commands. So, without further ado, let's get on with it. Okay, so this follows directly on from part 2, a link to which should be appearing somewhere on screen. I don't know where it'll be, along the top somewhere. We start with this board here. This is the AT-Tiny85 base circuit we built in episode 1, extended in episode 2, the circuit diagram for which is here, so I'll just put this down here where we can see this. This currently just flashes this little red LED, move up so you can see the LED, flashes this little red LED here. When it's connected to track power via these orange and black wire, which represented by this part here up on the circuit. It's not a bad foundation to work from. What we've got on here is a stable power supply, provided by this LM7805, giving us 5 volts. We actually have a DC power supply, which we can tap off here. It's not on the diagram because we haven't done it yet. And we have a functional microcontroller. Now I'm going to be the first to admit, and I'm going to get in first because if I don't, the crush will get me. This isn't that useful. I mean, it could potentially be useful if you wanted to flash an LED or flash several LEDs. Yeah. So what we're going to do is we're going to modify this circuit, and then we're going to modify the code. So yes, this one is going to be a little bit code heavy again. Into a working function decoder. And what we're going to do is we're going to control 4 LEDs for now, which we've got sort of lurking over here, ominously at the sides, waiting for me. Now, this is going to be fairly straightforward. A later episode, like I say, we're going to take this a little bit further. At the end of this episode, though, we'll have the working device. Now, that could be taken in a number of directions. There will be source code in the description. There will be a full circuit diagram of where we're going to get to in the description. Yeah. Now, there's been a few comments on the first 2 videos worth addressing. I mean, my serious thanks for all the comments on this. These 2 videos have done far, far better than I expected they would. Firstly, AJB2K3 commented on the first video, pointing out that I said, if I can just get hold of it, it's out of the way over the side here. So much for preparation. Yeah, a servo attached to it as well. I said that this bit here is an ESP32. Now, yeah, AJB2K3 correctly points out this is actually an ESP32 module. The actual ESP32 chip itself lives inside this thing. It is small. It is about the same size, if not slightly smaller even, than this, which is the Atmega 328P on an Arduino Nano. So it's quite a small chip. It needs various other components to work. It needs the antenna on the end here or another plug-in antenna to work, so usually you use these little modules. It is, however, a valid point, and if you've got the right skills, which I don't, you can use the ESP32 chip directly. And it's actually very small. It's very powerful. It's very small. These little modules, they're not that big, but they're a little bit big for what I'm doing here. So that, yes, so that is technically correct. User Timbersurf noted, let's get this out of the way because we don't need this one, that I'm using a standard bridge rectifier on here. And I am. It is a DB104. I thought it was a DB102, but it's actually a DB104. This is a 4 amp rectifier. What we actually need here is a fast recovery bridge rectifier, which I don't actually have. I hadn't thought about this, so thank you, Timbersurf. This is what happened here. This can actually cause distortions in the DCC circuit. So yeah, this series is using the rectifiers I've got. When I go to an actual circuit board, however, I'm going to get some high-speed ones, which should sort out any gremlins. I've not noticed any problems yet, but I just know if I build a load of these into a circuit, I will. And A final point, AJB2K3 again noted, I commented I was getting on this thing. I said I got in 5 volts from USB, I was actually getting about 4.8 volts. Now he's quite correctly noted, she, I don't know actually, anyway, USB is 5 volts, so what's going in here is 5 volts, and if it's not, you've got a problem. Usually what it means is you're drawing too much current and the power supply can't keep up. You should unplug things before you damage anything. What I actually meant was on the 5 volt output line. Now it's an input and an output. But on the 5 volt output line I was normally getting 4.8 volts when it's powered through USB. There is some internal circuitry within here, including a diode which protects it, which drops a little bit of voltage. That's what I've seen. This is the effect I was referring to. I'm sorry I was not being entirely clear on that. The main thing it manifests itself is things like LCD screens, as we saw in earlier videos. There is a contrast adjust on there, and it depends on the voltage. And what you find is if you power it off USB and use this 5 volt output, you can adjust the contrast to be what you need. And when you power it off 5 volt, you have got to adjust it again. It's just one of those little bits and pieces. The other thing that he notes very, very correctly is if this is plugged into a USB port, do not power 5 volts this way. One of the things I've done on some of my other little project boards is this little link is actually a diode, which further drops the voltage on here. I use a little Schottky diode, which drops about 0.2 of a volt, I think, usually. Yeah, and what that means is if you do power up over here, it can't feed back and power the nano, which is a sort of way of protecting it when it goes this way. What I usually do is actually put it in the other way round, so that the nano on USB powers the nano, but nothing else. There's usually a whole load of other circuitry off this, and what I don't want to do is overload this thing's power supply. Anyway, enough of that. So let's get back to the video, and the first thing we're going to do is we're going to work on the input stage. Okay, so an input stage. Now, this circuit's actually very, very simple. There is a little bit of a caveat on how it works. A little bit of explanation on how it works is useful now, but firstly, the important note. What we're about to do only works if you are going to use DCC track power to power your device. If you're going to try and measure the DCC track power and you've got another 5 volt supply or 12 volt supply or whatever else you're using, this method won't work. Not only will it not work, it's quite likely to blow things up like your little chip. So this is because of the way voltages work. So let's just have a little look. Now, what do we mean by voltage? So what we've got, I'm going to draw a resistor here, but it could be anything. A and B. Now when we say volts, what we're talking about is a potential difference. Now if you're not interested in the theory, feel free to skip ahead until we get to the little circuit. But this will show how this actually works. Useful to understand. So what we mean, when I say, let's say 10 volts between A and B, well that could be 10. And that could be 20. There's a 10 volt difference. Normally what we do is we'll set one of these points, and convention is you draw it on the lower part of your board to be 0, and then that is plus whatever your voltage is. And that's what you do. And you think, well, that's quite nice. So here, what we've got coming out of the rectifier circuit, so that sort of sits over here, and I'm going to put the DCC that way, and we've got a plus and we have a minus, and coming out of this we're going to use this minus, something under here. What's under here? Have a little look. Just a biscuit crumb. Anyway, and we're going to take this minus point down here and we're going to call that 0. That is our reference point. Now on this circuit I know that is 13.3 volt. You can measure across there. It's 13.3 volt even if they're not connected. There's no current flow at that point, obviously. So there you go. And then we're going to take that and we're going to put that into our little rectifier stage, the rectifier, the little regulator. And there we've got 5 volts. That 5 volts is 5 volts relative to the same ground. This has even got a ground connection in it, so we can just do that. I'm not going to draw the capacitors. So that's good. And this DCC waveform here, it isn't AC. It's a modulated DC signal, but that's, yeah. It's measured at 16 volts. But it is an alternating waveform. So it's either plus 16 and naught, or plus 16 and naught. It's just how it works. You could put a center point in that and say plus 8, minus 8, and have a ground in the middle. There's various ways you could do it. But now, say we've got over here, I've got another power supply. And it's got 5 volts and it's got naught. You think, oh, brilliant. Well, I'm going to power something off this. Now, the thing is, these two are entirely independent. So that 5 is relative to that ground, not this one. Relative to this ground, that could be 5, it could be 10, it could be minus 5, it could be 50, it could be anything. The point is you don't know. So if we're going to use this system, which is what we're using, we've got a ground reference. But say we put our little microchip over here, and we want to feed in this signal, or this signal. Say we're going to take this, and we're going to bring it all the way around here, and we're going to feed it in. We don't know what that voltage is, and because we don't know what that voltage is, we can't adjust it to make it safe for this. Because it's not even a case of you could measure it and work it out. It might change. You don't know. And if these ultimately come off the same power supply, it's probably not going to vary by much, but you don't know. And if you're going to do that, what you have to do is use a little chip called an opto-isolator, which, for want of a better word, a better thing looks like that. And if you've seen my little photo interrupter thing that I'm using to detect trains, that's a form of opto-isolation. What you've got is on one side there's an LED, the other side there's a photo transistor, and instead of a train we're going through the middle of it, there's nothing. So the light lights up in this, but the thing is they're electrically isolated. Anyway, this is why if you're going to have a separately powered function, you've got to have that isolator in there, because you don't know what the voltage is. We will look at that in a later video, but we're not going to use it here because it takes up more components and it's a little bit larger. So with that out of the way, what are we actually going to do? Well, we need to feed the DCC waveform into the ATtiny. What we actually need to be able to do is detect the change in logic level at some point, and I'm going to put it over here. It's going to be pin 7, which is going to come out of here, and this is GPIO2 on the chip, but it's pin 7. What we need to do is feed this a voltage, and it can't be any more than 5 volts, because if it's more than 5 volts we'll blow this up. And it can't be any less than 0. Well, I can go a little bit less, but not much. Between 0 and 5. Whereas over here, that's 16 volt. But we know it's 16 volt because we're using the same power supply, so we have the same ground reference that's being generated from it. Now the chip itself, and this is why we're using this pin on GPIO2, has got hardware built in that can detect a signal. Let's come up here where we've got a little bit of space. It can detect a logic signal doing that. Changing from low to high. You think, And there's hardware involved. It's an interrupt circuit, and it says, that happens, do something now. And then later on that waveform's going to drop, and it's going to do that. And we're going to go, aha. And the way DCC works, it varies that distance. There's 2 parameters. If it's less than a certain value, it's a 1, I think it is, and if it's more than a certain value, it's a 0. And in practice, some of it, you end up with circuits, waveforms that look like that, or they can be like that, and some of them, it'll go a bit longer when it wants to. So, we've got here, we've got a 1, there we've got a 0, and then you carry on. And that's how it gets the signal in. But that's between 0 and 16. We need to step that down. So how do we do that? Well, it turns out it's actually quite straightforward. Inside here, and I'm going to draw it on the circuit, but I'm going to do it with a dotted line. In here, there is a pull-up resistor, and that goes to plus 5 volt. We don't have to use that, but we're going to. And it's about a 50k resistor. It varies. But if we connect that, excuse me, we turn that's on. At this point, that pin is now at 5 volts. This is useful because we can actually say, well, if I drag that to 0, nothing will happen. We've gone on this cycle from 5 to 0. But when I release it, it'll go back up again, and it can detect that. So what we need to do is have a circuit that links this point to over here. And because we're using the same power, I've got to emphasize this again, because we're using the same reference point, what we're about to do works. Now, this is actually partially why the video is a little bit delayed. I know what I need to do here, but I wanted to try and get my head around how it worked. Because what we're going to do is we're going to come along here and we're going to put in another resistor, and it's going to be a 10k resistor. Doesn't have to be a 10k resistor, but we're going to see why in a minute. And we're going to come along here and we're going to put a diode in. Not a light emitting diode this time, just a diode. And that is, if I can find the pack of them, a 1N914. Doesn't specifically have to be that diode, but it has to be a signal diode, a fast recovery signal diode. This is the sort of, up here should be fast recovery rectifier diodes. And what I'm going to do is I'm going to come over here, I'll move my hand out of the way in a minute so you can see what I'm doing, and we're going to come across here like that. But that's 16 volt. That'll blow it up. It won't. There's two states, and we're going to look at this little point here, and we're going to call that voltage in, and I'm going to call this point here X, and I'm going to call this little point here Y. Now there's two states. Case 1 is over here. So I'm just shift this bit of paper up a bit so when I'm writing down here you can see what I'm doing. And in this case, V in is 0. This is the low part of the waveform. So what happens? Well, this means this point here is at 0. So we're going to get a current flow through there to down here because that's what the diode allows us to do. But we want to know what voltage. Effectively X is actually there, but it feeds in. That's the point the chip sees. So what happens? Well, point Y will be 0.7 volts because across that diode is 0.7 volts. Okay? So Y equals... I've got more stuff under here again. So this is I use this mat for modelling on. It's got bits all over it. Anyway. But what's X? Well, we're going to come over here a little bit. And just... This is what we've actually sort of got. And this is a potential divider. So up there you've got V in, 0. You come across there, V out. And you have R1 and you have R2. And V out, and this is electronics, mathematics stuff, is, I'm trying to get which way round these things are, is R just trying to remember which way around this goes. R2 divided by R2 plus R1, then all of that multiplied by your input voltage. And this it's a very simple way of getting a voltage. There is a little bit of a gotcha. Typically you've got a thing here. That thing has a resistance of its own, so that affects this one. So if you know what that load is going to be, you can split voltages like this. And typically you use this with what's known as a high impedance load. So that is, it's not an infinite resistance, but it may as well be. The AT Tiny is high impedance inputs. That'll be a couple of mega ohms, basically very, very high value. So it doesn't really affect this. So you can come up here and you can say, well, I'm going to put a 10k there. I'm going to put a 10k there, and it'll come through here. And then what you end up is 10 divided by 20, or a half. So if that was 5 volts, you'd get 2.5 volts there. That's what a potential divider does. Now over here, excuse me, we've got a 50k and a 10k. And what this means is our X point, which is here, will equal, and I've written this out before just to make sure I try and get it at least remotely correct, 10 plus 50 ding, ding, multiplied by 5 minus 0.7, because that's always going to drop. If there isn't enough voltage to drop that, it's not going to work. So that's how that one works. And what we're going to end up with at that point is X will be at 0.72 volts. And if it's below about 1.5, that is logic low, which means if it was logic high, we'll see this transition. Case 2, fairly straightforward. V in equals 16 volts. We're now on the high side of the waveform. Well, at this point, this side here is higher than this side here, which is at 5. So no current will flow through that. So we can forget that bit of the circuit. And in that particular case, Y is 5 volts and X is 5 volts. And that will be seen as logic high. And that's how we're going to get our two little voltage bits through there. And what it means, and it's quite straightforward, we can build our little input stage circuit, and it's that. It is literally a diode and a resistor. There are the reasons you choose this. This value has got to be sufficient that when you put it through this equation, you get a low enough voltage. Basically, the lower that is, the higher this voltage will get. But you don't want it too low, because you are still trying to limit current. Because when this is at low, you are going to feed some current back this way, which is going to go back into your DCC system. You want to keep that as low as possible. And here it's 5 volts going through 60k ohms. It's minimal. Well, 4.3 volts going through that 60k through that. So that one works. Now, that is a very, very simple thing. Now, as we say, that needs to be a fast acting one, which we got. This will pick up. Yay. Right. That's enough theory. So what we're going to do is we're going to actually add that to our little circuit here. Now, this requires me to find my tweezers, because these components are quite small. And what I'm going to do is I'm going to start off with a 10k resistor. You can actually do these either way round. I'm going to put the 10k this side, because if I put the 10k this side, life gets a little bit easier to see what I'm doing. So I'm going to put that. Just trying to see where the legs are going. Get in there. Right. So that is a 10k resistor, and it's just coming straight off this black side. It's coming out, and it's coming to the row adjacent to this thing. So what I'm now going to do is put this in. And diode, you have to get it the right way around. So there's a little stripe. That's this end here. So that goes in. Again, just flicked out the things. I'm using tweezers to help with it. I'm going to try and just put this one in by hand, see if it goes in. Get in there. Right. That goes in next to it. And what we now need to do is link that all the way over here to pin 7, which means I go there to there, like that. And with that, that's the hardware for the input stage completed. Right. Programming. Right, so as we say, the next step is to program this thing. Now to do this, we need the Arduino IDE, which we have, and we've got set up to work with the ATtiny 85 series. We now need to add a library, so we go into here, and what we want is NMRA, type it right, DCC. Now I've installed this already. This is the library you want. This does all of the hard work for you. That's the library you want. It's really rather useful. So we start off with include NMRA DCC.h. So there we are. We brought that library in. And there's a few things we need to work with here. So what we're going to do, this is up at the top. We need to tell it what address we want. We are going to tell it what pin we have put the input onto. Remember, this is GPIO 2, which is pin 7 on the actual chip. And what we've now got is an LED, which we're going to set up to be a light LED. Now this is on pin 0, so this is our red LED. It'll come on when we're going, tell the thing we're going forwards. You may think, why would you have a red LED coming on forwards? Well, this is going to go into a coach. When the thing is in the forward direction, I want the tail light to be on. So, yeah, anyway. We're now going to pick up some examples. Now, this is drawn from, as I say, an example supplied with a library written by Alan Shepard. So, my thanks to him. This is where I'm lifting bits of this from. I've modified it slightly. One of the examples I found, there was a slight, it's not really an error, it's a slight omission. So I've modified a few bits and pieces. So what we're going to have here is code that says previous and current state for the LED and then for the direction. That works. We've now got to do a little bit of C programming language wibble. And what this does is we are going to create our own variable. Don't worry too much about how it actually works, but what this does is this creates something. So we can say, instead of like uint8t, we can say cv pair. And it's a structure which consists of a 16-bit value and an 8-bit value. The 16-bit value is going to be the CV number, so yeah, it's a CV 1, CV2, CV3, yada yada yada. And because it goes up to above 256, or yeah, there's 0 to above 255, we need to be a 16-bit value. I think it goes up to about 500 and something. So there we go. A little bit wasteful in space is what it is. But what we now need to do is decide what our initial CV values are going to be. So what we're going to do is we're going to create an array of these. And the first one we're going to put in is we're going to tell it. So this define a CV multifunction primary address. So that is our CV short address is what that means, and it's going to be set to be 3. We now want to set the long address, and to do that we have to set 2 different values, and the library comes with some functions to do that for us. Really, really useful. And what we're now going to do is configure CV29, which is the only other one we need at the moment. And we're going to say on that, so this is going to be CV29, and we're going to set 2 bits in it. One is we're going to tell it we want to use the long address, and this location bit at the end tells it we want to use 28 or 128 speed steps. And that's that. Next, we need to create the actual object, which is our library. So there we go. We're going to create an object, get rid of that space. So we're going to have an object called DCC, which is basically the library object. We also need a global variable here, which is the default CV index of 0, which would be that first one. This is useful because we're going to come to a little bit of code. Change that because that annoys me. I know that other people like putting that, it irritates me. I prefer it that way. Yeah, we're going to go through various things and we're going to see what we do. There is a gotcha here. I will come back to that. So that's what we're going to do. We're going to say it's address 3 using long addressing. There we go. So what we now need to do is we need to create a couple of functions here. Now we're not going to use them all, but that we've got to have them, because if we don't, it won't work. And the first one is this, and we're not going to do anything there. This will be called, and I'll put a note in here, called when a CV value changes. We're going to have the ability to change CV values on the programming track or on the main track. And if that happens, this little bit of routine is going to get called, and it's going to say CV number 12345. Won't be that high, but you know what I mean. Is now value such and such. I think brilliant. Now the library will store that already. Don't have to do anything with that. It will store that in the electronically erasable programmable read-only memory on the little 80 tiny chip. Read-only memory, as the name suggests, you can only read it, you can't change it. Programmable means you can change it, but you can only change it once. So you can change it to be something and it stays that way. Erasable means you can also wipe it. This used to be done with a little ultraviolet window. You shined ultraviolet light on it and it would wipe it. So you have a little sticker on top of the chip you'd have to take off. And then the other E for electronically means you can do it electronically. Think of it as it's memory that stays when you turn the power off, so it's quite useful. The next one we're going to put in, and this one is going to do something, is we will get this one here, which is a notification when the speed or direction changes. And this one's a little bit interesting. We're going to store the direction. That's all we care about on this. This thing doesn't respond to speed, it just responds to direction. So here we have the direction. As you see, we get the speed, we get the number of speed steps done us. We also get the address. You're thinking, well, what do we need the address for? Do we have to do something with this? You can tell the library, and we'll come to this in a minute, that I only want my own messages, in which case you can just respond here. Or you can say, I want them all. In which case you would have to do, well, does this address meet my address? But what this means is you can have a decoder connected to a locomotive, and it can have its own address, but you could tell it, by the way, the locomotive you're connected to is number 1234. And in here you can say, well, if my address comes up, listen to it, but I might also want to listen to 1234. You can. You don't have to. You can do it the simple way. But that works. And now what we've got to do, and this one's slightly more awkward to do, not by much. We put this in here. This one here is notification. So function state has changed. This is the user has pressed function 1 button or function 0. So this is going to come through and we're going to tell it we want to do something if that happens. The way this comes through is a little bit odd. Function group is a value. So function 0, 1, 2, 3, 4 are in a single group. And different bits of the value respond to what we're doing. So what we're going to do is in here. We're going to put this in. So this is function state, which is where the data is, logical AND with function bit 0. This basically says if bit 0 or whatever that bit is, that's the bit we want. We're going to get rid of all the rest of it. We just want that bit. And this little operator here, this is a trinary operator. It's a shorthand for an if statement. What this basically says is if that is true, respond with a 1. If it's not true, respond with a 0. So this is going to set the new LED state to whatever the state of function 0 is. I think, oh, well, that's useful. And now we have another one we have to do. And this is where we hit a bit of a problem. This is how we, this is how we respond to us reading a CV. We have to try to type and write at the same time. Now the NMRA spec says what we need to do. And what we have to do is turn something on, wait 8 microseconds, and turn it off again. But what we've got to do is switch on at least 60 milliamps of current. Now that's going to be a little bit problematic because if we go back to here, all we can switch on and off is this LED, which with a 1K resistor and 5 volts, that's about 3 millivolts, 3 milliamps rather. So this isn't going to work. Now I can tell you now, this is not going to work. But we're going to carry on with it anyway, because this is only for responding back on a programming track. We should be able to read this and have it run quite nicely with our address 3 and turn the light on and off. Until we, all this means is we can't say, put this on a programming track and say, what address are you? I think brilliant. Okay, so that's enough for the configuration. What we need to do now is go into our setup section. We're going to tell it that that pin is an output. We are then going to I'll bring this in like so. We need to initialize, well, it's not fully initialized, so set up DCC object with the pin. So this is saying I want to use pin that we've defined up above here, which is defined as pin 2. That one says I want the internal pull-up resistor connected. You could add an external one, but to be honest, we're trying to save space. So while I do like using external ones, I'm not going to here. What we now need to do is initialize that library. And what this is saying is we're going to set the ID. I think that sets a factory value, ID value. This is where we say I only want the addresses, the stuff that's addressed to me. And this bit is very important. What this bit means is if we set CV7 and CV8 both to a value of 255, this is going to call a reset routine. And the reset routine it's going to call is, where are we? Let me just find this. I've got to drag in as well. So there's one I forgot. This actually goes in up at the top here. Goes up here. And what it'll do is it'll call this one. And all this does is it sets that default index value to the size of this array. So it'll set it to 4. Because we've got 4 lines in here. I think, oh, what's that going to do? This is where there's a little bit of a gotcha. The original code had that in, but it misses quite an important part when we get down into this next section. Now you can call that function straight away. And you think, well, why would you do that? Well, this is where the gotcha comes in. We've said I want this here excuse me, to be my default CV values. But nowhere are we actually setting those. But we don't want to set them you can set it here, but if you set it here, what you've got to do is program this. You've then got to run it, and run it as in on the track. It will then power up and it will reset and it'll set those decoder bits. You've then got to take it off the track. You've got to take the chip out. You've got to reprogram it with the line here turned off. And it's just a bit awkward. So I'm not going to do that. I'm going to show you another way of doing it. But now we come down here into the loop function. And what we have to do, and before we do anything else, is call this. And this allows the DCC thing to monitor. And it's looking for commands. It's important to note you have to call that often. Now, I'm only going to call it once per loop because we're not doing much in the loop. If you were doing a lot in the loop, say you were trying to update screens and other bits and pieces, you'd want to call this quite a few more times because otherwise you miss bits of data. But now what we're going to do is get the reset working. Now this is the code bit. It was missing from the example I lifted this stuff from, but it's in all of the other ones that Al Shepard's put together. So yeah, I'm guessing it's just a typo, but it doesn't matter. So this is a routine here. Now what this is going to say is if that value isn't 0, remember we set it to 0 by default, but this code up here sets it to the size of that array. So it'll say, oh, well, it's 4. And we're ready to set a CV. Oh, that's useful. Well, the first thing we're going to have to do that's a decrement. So we're going to start with, we've set that up to be 4, but because the array starts at 0, we have to say I want it to go down 1. So now that value is now 3. And what we now do is we call this function, and this stores the CV value from our little array above and stores it into the EEPROM. Brilliant. And it only does 1. Yeah, well, why would it only do 1? Well, because it takes a little bit of time to write to the EEPROM, there's a routine that says, well, is it ready to write another bit or another byte? And if it isn't, it'll just skip through. So it'll say, oh, well, that's now on 3. I've done that. Might go through and miss a few loops and go, right, we're now ready again. So I'll drop it down to 2 and I'll write that one. So it can take a couple of program loops to actually write this. But that code is how you do the reset. And all it was those lines were missing. So those lines are now in. This caused me no end of frustration when I was trying to work out why I couldn't get bits of this to work. It was storing. See, when I first put one of these, let's go back to this here. When I first put one of these, because I've got another one, which is the one I showed in the original video, on the programming track, and I got it to respond, which we'll come to later, I could program the address and it would respond to it. But the defaults I was setting, none of them worked. It would store whatever I set it in Decoder Pro, but it didn't work otherwise, which was perplexing me. Anyway, so I got that. So what we're now going to do is we're going to come into here and we're going to say, right, let's have a little look at if we've actually had some information here. So we're going to come in here and this is what we're going to look at. So is the new state of the LED, remember we will set that in this function up here and we'll set the direction in this function up here. Have either of those changed from what they were before? If so, we need to do something. If they haven't, we don't care. I think fair enough. So what we're now going to do, start off, we're going to come in here and say, well, if the LED is to be set, do that. And what this means is if the new state is on, and this is Otherwise, if the new state is off. So if the new state we want is on, what we're going to do is turn the LED on. Brilliant. Excellent stuff. Love it. I'm going to come down here and we're going to go turn the LED off. Fair enough. That works. And we're not at the moment too fussed about the direction. Nah, sod it. Let's put the direction code in as well while we're here. Why not? So this here comes into this, and we go here, and we do it this way. Kadink, like that. I'm just trying to think of get this the right way around. So this is going to be forwards or reverse. Yeah, so so that is forwards. We have an L. Yeah, let me type it correctly. Here we have an else, which is reverse. So now copy there, right? Take that away. So if we're in forwards, just get the indenting right. We're going to do that. But this says we only do this if the LEDs are on. If the LEDs are off, what we're actually going to do, so there, is turn it off. Whereas if we're in reverse, we're actually going to do the same bit of code, with the exception, get that back, we're always going to turn the LED off, because the LED only wants to be on if we're going forward. So I'm going to put that there, if forwards and LED on, which is actually F0 on, light on. And in all the other combinations, we're going to turn the light off. And that's it. So, what we now have to do is program it. And because I want to show how this works properly the first time around, I'm actually going to take this ATtiny out of here altogether. I'm going to put it back in its box. This is because this one has been used. And because I've used it, the EEPROM is set. So it knows what its address is. Now this, so I'm going to show you what happens when you have a completely new one of these. So I'm going to just turn this around the right way. Plug that in the right way, and go into there like so. Now I now need to find the appropriate lead, which is this one. So that goes in. It will go in there. There we are. You can always get it in the hole eventually. Snigger, snigger, snigger. Anyway, there we go. And that goes into that. So that powers up. This is now ready to program. Now, remember, this is the first time I've used this thing, so I have to come up here. Let's just go back into this one. Actually, put it back on that one there. So the first thing I have to do is burn the bootloader. And that sets the internal, they're switchable fuses. That tells it I want to use a 16 megahertz chip. Sorry, the 16 megahertz internal clock. Right, now we can upload the actual code when it's going to fall flat on its bum, because there needs to be a semicolon there. It's going to work. And it's blinking away nicely as it programs it. Incidentally, the red light will come on if it generates an error. Finished. Right, so I can now unplug that again. We can take this out of here. I can bring it back to this. It goes in. Get lined up. Goes in there. Now, this should now work. this is what I mean, there's a gotcha. This won't have the default CVs set, so we're going to go downstairs and we have a little look at what we've got. So, to the cellar. Okay, here we are. Now, this is now connected. So, turn the power on. And the power comes on. Now, this is connected by ramming wires underneath things again. So, first off, let's try identifying it. First thing I need to do is switch the track into programming mode. Like so. What I'm now going to do is click identify. As you can see, the light is flashing. And I have a message here, stopped due to error, no acknowledgement from locomotive. Now this is because the little thing can't detect, it's not drawing enough current to detect it. You think, well, okay, that's fair enough. So, back to main. Let's just try driving it manually anyway. So what I'm going to do is go actions, new throttle. And this will load up. I'm going to say, well, we've told it to be throttle number 3. So let's set that. And let's try turning the light on. I've used this chip before. I didn't think I had, but I have. This one's actually loaded up quite nicely. But as you can see there, I didn't think I'd use this one. I've obviously used it because it's pre-programmed itself. But we're controlling the light. Right. Now, assuming that hadn't worked, how do we reset this thing? So we come up to here and we go single CV programmer. Now put it back in program mode. Now remember, the thing can't respond. Doesn't matter. So what we're going to do is set CV7 rather, to 255. I'm going to write that. There we go. And I'm then going to tell it to do the same to CV8. Going to write that. Right. That should now have reset this decoder. So I now go in here, and then what you do is you go in here, new throttle, you go number 3, set, and now it's not working because that reset function hasn't worked properly. Right, anyway, what we need to do is read these things back, which we can't. So we need to go upstairs and we need to change how much current we're drawing. So I'm going to turn the track power off and we are going to go back upstairs to the desk. Okay, we're back. So what we have to do is increase the current draw. This feels seriously wrong. Normally I try to minimize current draw, but here I need at least 60 milliamps. Well, there is quite a simple way of doing this, which is to add more LEDs. So what I'm going to do is I'm going to stick... try and work out where to put these. First thing I need to do, if I just put 4 LEDs in, I'm trying to remember which order round I put these in. I think they go, one goes in there, like so, and the other 2 go up at the top, which again makes a little bit more sense. So yeah, 1 there. Again, get these the right way round. Red and green are the bottom ones. Yeah, I pre-did this and I've got all the legs bent in the appropriate directions. So there we go. So that can go there. And what I also obviously need to do is hook up some more wires. So I'm going to say this green LED is going to go on this pin. Now we're going to have to program these all to work. Needs a resistor. We'll come back to that. That yellow LED is going to go there, like so. And the blue one is going to be there, like that. What I'm going to do is we come over here. So I now have another one, which is pin 6, and that's GPIO 1. And I've then got round here is pins 2 and 3, 2 and 3. And I can't remember which of those is which. One of them is 4. I think pin 2 is GPIO 4. I think that one is GPIO 3. Not 100% sure which way around they are. Anyway, what we're going to do is we're going to put a resistor on each of those. They're going to come off here. They're going to go to LEDs. This. They're going to come off over here like so. Now normally, as I said, I try to run... No, down to ground. I try and run LEDs on low current. So I can put in a load more of these little 1K resistors. However, what that'll mean is I'm switching about 12 milliohms. Yeah, that's sorry, milliamps, not milliohms. So that's not enough. So I'm going to take that out. And what I'm going to do is I'm going to put in... which ones have I got? 150 ohm resistors. Now on the red LED, and it does vary slightly between the different LEDs here, that's about 20 milliamps. The LED will cope, but you'll see it's brighter. You'll see when people say you can't control resistor brightness with, LED brightness with resistors. Oh yeah, you can. Yeah. They light up in proportion to the current going through them. So limit the current, away you go. So, there are LEDs that will be extremely bright on low current. These, however, are extremely cheap LEDs. So if I put that into there, so instead of being 1K, they're all 150 ohm. So between them, it won't be quite 80 milliamps, but it'll be more than 60. So what we need to do now is adapt the code. And this is relatively straightforward to do, but we're actually going to do we're going to do it a little bit differently. We're going to add a little bit more functionality in here. So what we're going to do is we're going to come up here and say that is going to come on. But while we're at it, why not respond to F1 and F2 as well? Now, what this is going to give us is a headlight and a tail light, which are going to be these down here, the red and the green. Red comes on when we're in forwards, the green's going to come on when we're in backwards. These two are going to be switchable via other functions. You think, cracking. So, what we now need to do is... I'm just scrolling. I'm going to be copy and pasting code that I've already written, not fairly obviously at this point. So we're going to come down here into the startup code, so the setup code, and we're going to tell it those are more LEDs. Yeah, right. It's fairly straightforward. We do need to add a few more variables up at the top. It's nothing too serious. New LED state direction. We need to know the state information for function 1 and function 2. And that's it for that bit. We have to come into here and we need to add a little bit more code because we need to respond to functions 1 and 2. That'll do. We've still got the direction code up here. And then in this notify bit here, what we're going to do is switch all of them on and then switch all of them off, and that should be enough current to make this work. So what we're now going to do is we're going to come down here into this bit of code here, and I'm just going to delete all of this. Take all of that out like that, and I'm going to replace it with slightly different code. So this is the directional code. So what we have now is this bit. It's purely directional. Delete that. And what this is going to do is if we're in forwards, we do such and such. Otherwise we do such and such. Otherwise we turn the lights off. So here we have, we go in. So we've got, we're doing something here, and we're just going to turn the lights off otherwise. That works. Now we need to do the bit for the other two lights, which are done independently. Now, we can just write out, we're storing a 1 or a 0 for the light, so we can just write that out. But that's that. So what I now need to do is take this little chip out of here again, because it needs reprogramming again. So take this out. There is a way to program these things in the circuit, but you have to design your circuit carefully, because you start getting to the point of, well, you don't really want to use the programming pins for anything else. Or you can, but you've got to be careful with it. So let's upload that. It doesn't like that. What have I done here? That one there, that one there. I've got a line missing here, which is this bit. I thought looking in I might have copied something incorrectly, and I have. So this is basically, if the lights are on, do this thing below it. There we go. It should go nicely. There we go. And the yellow light goes bananas as this copies over. It says thank you because it's finished. Thank you very much. So that can come out of there. Again, pick that up. Little chip out of here. Incidentally, don't put these in backwards. Ask me how I know, but they get very hot. If you catch it quickly enough, it does still work, but I wouldn't recommend it. So, that is now set up. So we've got a higher current draw. You'll notice when we set up this LED, it will be a lot brighter than this red one. This one's still on a 1K resistor. But, back to the seller. Right, now we're back. It's plugged into the programming track. Turn the power on. You can see the power light comes on. Let's now try and read it. So we do this. You can see the lights are all flashing, and you can see how much brighter that red LED is. And on the screen here, we're now reading different CVs, which is coming in quite nicely. And it's picked up. This is my Tiny85 test profile. Okay, well, let's have a look at programming it. So we're on here. Let's read all of this. Well, this is where these LEDs start flashing as it reads. And what we can see is we've got address 3, which is what we wanted. We're in 128 speed step. It's set up to be digital only. I love how it says the default is both. The default is actually DCC only. As far as I can tell, it's digital only. You've got to set a bit to be 1 if you want to do both, but there we go. We have manufacturer ID and version number, which is basically tells us this thing here. So, that works. Well, let me just save and close that. We can write and change those incidentally as well, but we'll look at that in another video. So, actually no, let's do it now, because I can. So what I'm going to do is I'm going to go into this here. Again, read that sheet. Goes through, reads it. What I'm going to do is I'm going to set the address to be 4. Try that one. So we write that, and we go away. I close that. It'll tell me do I want to save it, so I will. What we're now going to do is bring up a throttle. Now remember, this is now address 4. So do that, set. Now the big one. Turn the lights on. Sorry, my fault. I need to put the track into run mode. Because programming mode, it won't give it enough current to do anything. So turn the lights on. There we are, we have our headlight. And again, notice how much brighter that is. We change the direction. So we have a directional light. We can control the blue light as F1 and the yellow light as F2. Now at this point, we have a somewhat functioning decoder. It's far from perfect. It's on address 4, which I'm actually going to reprogram back to being address 3. So just flick it back into programming mode. We haven't really at the moment got the ability to program it to do anything else. So release that, get rid of that. Program. Reason being, it doesn't do anything else at the moment. So yeah, so I'm going to tell that to be a 3, and tell that to be a 3. Write that. Oop, no acknowledgement from the locomotive. It's flashing away quite nicely. And the reason it's not doing that, I know why it's not doing that. Turn the power back on. It's because one of the LEDs was on. And because one of the LEDs was on, it couldn't pick it up. Because we didn't have enough of a current to change. So if I now tell it to write, there we are, done. 4, put it back to 3. Now it's interesting, it actually sends out the commands. So even when you say write, it sends out the commands to write them, but if it doesn't get a response, it's not happy. So again, let's just bring up a throttle and just check that. Put it back into main mode. Lights. Yeah, they work. Now, conclusion. So at this point, we have a very basic function decoder. I'm just going to sit here and play with the lights because I can. Based on the ATtiny85. Accepts on-track programming for a couple of CVs. So far, only the address really does anything in terms of a CV. And we can control 4 LEDs. Brilliant. Code for this and the circuit diagram are going to go on the GitHub. Link in the description for anyone who fancies trying it. Keep in mind you may well have to set the CVs up with the default with the reset via CV7 and CV8. Now, in the next episode, we're going to take this a step further. The LEDs are going to move up to being driven by transistors, and we're going to put them on the 13.3 volt circuit. What this will do is cut the load on the ATtiny and the voltage regulator while maintaining the required amount of current for the programming system to work. We're going to look at varying the brightness of the LEDs using the analog right pulse width modulation. We're then going to look at using a CV to control that brightness so we can program it. So instead of being sort of eye-searing brightness on some of these, it'll be a bit dimmer. And then possibly using a custom CV so that we can have another function, maybe function 3, that says I want the lights to be bright or I want them to be dim with 2 programmable settings. As well probably as honouring the direction bit in CV29, which currently doesn't do anything. If I tell this thing to reverse, it doesn't do anything because the chip doesn't know how to. Anyway, for now though, that's it for this 3rd episode. As always, likes, shares, comments, subscriptions, more than welcomed. What do you think of the project so far? What sort of things would you use it for? Until the next one, enjoy the rest of your weekend. I'll catch you all around. Thank you very much, and goodbye with blinky lights.